Welcome to Unit 8 of this course. In the last unit, we saw what is called linear temporal logic, LTL. In this unit, we will see how one can check LTL properties on transition systems. In the sense, given a transition system and an LTL formula, what is the algorithm that checks whether the formula is true on the transition system or not. That will be the subject of this unit. In the first module, we will give an introduction to the algorithm. The algorithm is going to be based on Bucci automata. Here is the question. Given a transition system and an LTL formula phi, does the transition system satisfy the LTL formula? We have seen that a transition system satisfies an LTL formula if every execution of this transition system, in other words, if every trace of this system satisfies the LTL formula phi. So every LTL formula corresponds to a set of infinite words. What we need to check is the traces of this transition system included inside this LTL formula. There is another way of doing it. Consider the negation of this formula, not phi. We want to check if there exists a trace of this transition system that satisfies the negation. If there is a trace that satisfies the negation, that means the transition system does not satisfy the original formula. However, if no trace of the transition system satisfies the negation, that means every trace satisfies the original formula. Okay, so the question now boils down to asking, is there a trace of this transition system that satisfies not phi? This is going to be the question that we will ask. How do we solve this question? The first step, we convert this LTL formula to a nondeterministic Bucci automaton. We have not yet said how to do this. Assume that we have this procedure. From not phi, you get an NBA, A not phi, that is equivalent to not phi. That is, the language of not phi is the same as the language of this automaton. In the second step, convert the transition system to a nondeterministic Bucci automaton. We have seen how to do this in a previous unit. Just pass the labels on the states to the transitions, to the outgoing transitions. We now have two automata. This automaton captures the traces of the transition system. The language of this automaton is exactly the traces of the transition system. The language of this automaton, A not phi, is the set of all words which do not satisfy phi. The question is there a word of ATS which is also present in A not phi? Essentially, the question is the intersection of these two automata empty? L of ATS intersection L of A not phi empty. We know how to build the Bucci automaton corresponding to this intersection language. This was the modified cross product with flag which we had seen in the Bucci automaton unit. We have also seen how to check if the language of a Bucci automaton is empty or not using the nested DFS algorithm. So once this step is explained, the rest of them we have already seen. This is the schema for LTL model checking. Given a transition system and an LTL formula, you look at the negation, convert the negation to a Bushy automaton, convert the transition system to an automaton, and then check if the intersection of the languages of these two automata is empty or not. In this module, rather in this unit, we will look at the step of converting an LTL formula to a Bushy automaton. This is the goal. Given an LTL formula, there is a set of infinite words that satisfy this LTL formula. We want an equivalent automaton. That is, we want an automaton corresponding to this phi such that the language of this automaton is exactly equivalent to the set of words which satisfy the formula phi. In this module, we will start with examples. In the next two modules, we will give the actual construction. Let us assume that the set of atomic propositions is P1, P2. The alphabet that we are interested in is the power set of AP, the power set of P1, P2, which consists of the letter empty set, the letter consisting of the set P1, the letter consisting of the set P2, and then P1, P2. There are 4 letters in this alphabet. Let's start with the LTL formula FP1. FP1 gives us the set of all words where P1 occurs some time. For example, look at this word. P1 doesn't occur here, P1 doesn't occur here. Here P1 occurs, so this word satisfies FP1. Similarly here P1 already occurs in the first letter, so this word satisfies FP1. There are a lot of words which satisfy FP1, and the set of all such words will be the language of FP1. Now we want an automaton which accepts exactly this language. Here is the automaton. As long as the letter that is read does not contain P1, the automaton stays in Q0. The moment there is a letter containing P1, so there are 2 letters containing P1, either just the set P1 or P1, P2. The moment the automaton sees one of these 2 letters, it goes to an accepting state, and here it can read any letter and stay in the same state. That is denoted by the star. So the star denotes that it can be any letter, either empty set P2, P1 or P1, P2. Look at this word P2. So the automaton starts in Q0. When it reads P2, it stays in Q0. When it reads the empty set, it again stays in Q0. Again there is a P2, it stays in Q0. Now there is a P1, P2, it goes to Q1, and then whatever it reads, it stays in Q1. So the accepting, rather the run would be Q0, 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 Q1, 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 and so on. And since the accepting state occurs infinitely often, this word belongs to the language of this automaton. You can also show that any word that is accepted would have to have a P1. So this automaton represents the set of words that satisfy the property FP1. Let's now look at the other example, GP1. GP1 will give us the set of words where P1 occurs always. Look at this word. In every letter there is P1. Here also, in every letter there is P1. How do we give the automaton whose language is GP1? Simple, it has a single state, which is the initial as well as the accepting state. The only letters it can read are the set P1 and the set P1, P2. If it encounters a letter which does not contain P1, the automaton cannot read that letter. So this is a non-deterministic Duchy automaton. And the automaton has an accepting run only on the words that satisfy GP1. Let's move to the next example. Look at this LTL formula P1 and not P2. If you remember the semantics of LTL, these are the words that start with the letter P1. This letter satisfies P1 and it also satisfies not P2. So P1 and not P2 is the set of all words that start with this letter. You may recollect that giving an automaton for this language is not very difficult. This is the initial state. The first letter that is read is P1, the set P1. Then you go to an accepting state, and in the accepting state here you can read any letter because this formula depends only on the first letter. It filters out all words that have the first letter to be equal to P1. If you notice, I have marked this state as accepting as well. It's not needed. You could have started with Q0 being a non-accepting state, and then on seeing P1 you go to the state and read any letter. However, making this as an accepting state is not wrong either. I hope you understand that this automaton represents P1 and not P2. Let's look at P1 and X of not P2. That means words in which in the first letter P1 has to be true, and in the second letter not P2 has to be true. Look at this word. Here in the first letter P1 is true, and in the next letter P2 is not present. Here in the first letter P1 is true, and in the next letter P2 is not present. That is, not P2 is true. So here X of not P2 is true. So this is going to be the set of all words. Let us now try to give an automaton for this. The first letter it reads should contain P1, and the second letter it reads should not contain P2. Here is the automaton. The first transition is over either P1 or P1, P2. The second transition contains letters which do not have P2 in them. So they are just either the empty set or the letter consisting of the set P1, the singleton P1. Once you read this, the automaton can read any letter. Notice that here I have again made Q0, Q1 as the initials, as the accepting states. It's important that Q2 is an accepting state. Q0 and Q1 need not have to be accepting states, but at the same time, making them accepting states is not wrong either, because once you are in Q0, you read a letter and then go to the next state. From Q1, you go to the next state. The only loop occurs in Q2. Now, if you look at this word, you read P1, you read the empty set, and then you keep reading Q2. You keep reading a letter and staying in Q2. So an accepting state occurs infinitely often in that run, and hence the word will be accepted by this automaton. Let's move on to the next example. It is the same, except that we have added two x's in the front. It's x of P1 and x of not P2. That means you leave the first two letters, the remaining word should be satisfying this formula. In other words, the remaining word should belong to this. Look at this. Here P2, P1, ignore the first two letters, and then you have P1, P2. It satisfies P1 and x of not P2. Similarly, you ignore the first two letters. This one satisfies P1 and x of not P2. How do we give the automaton for this? It's similar to the previous automaton, just that the first two letters need to be ignored. So you read anything as the first letter, you read anything as the second letter. However, the third letter that you read should contain P1 and the fourth letter that you read should not contain P2. Once you do this, you read any letter. Okay? So this is the automaton for X of P1 and X of not P2. Let us now look at the automaton for P1 until P2. If you remember, P1 until P2 is satisfied by all words where sometime P2 is true and till then P1 should be true. Here P2 is true already in the first letter. Here P2 is true in the third letter and the second and the first letter satisfy P1. This is P1 until P2. Here is the automaton for this. As long as you don't see P2, you have to be reading P1. Okay, so P2 is seen either in the singleton P2 or in the letter P1, P2. Till you see one of these two letters, you have to be reading the singleton P1. Once you see one of these two, you can go to the accepting state. Here it is very important that Q0 is not an accepting state. Because if Q0 had been made an accepting state, then the word consisting of only P1s, see, keep looping around this, P1, 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 that would have been accepted. However, in the semantics of P1 until P2, we need to reach P2. And till then, P1 is true. So this should not be an accepting state. This is an accepting state. This automaton accepts words that satisfy P1 until P2. Let us now look at a slightly more complicated example. Instead of P1 until P2, it's going to be XP1 until P2. Firstly, note that this is not X of P1 until P2. No, it is XP1 until P2. At some point of time, P2 should be true. So look at this word here, position 0, 1, 2, 3, 4. Position 4 satisfies P2 and till that position, XP1 should be true. That means position 0, 1, 2, 3 should satisfy XP1. Let us check. Look at position 0. Does it satisfy XP1? Yes, because here there is P1. Look at position 1. Does it satisfy XP1? Yes, because here there is P1. Look at position 2. Does it satisfy XP1? Yes, because the third position contains P1. Similarly, look at position 3. It satisfies XP1 because position 4 contains P1. So 0, 1, 2, 3 satisfy XP1 and 4 satisfies P2. Now look at this word. P2 is true here in position 1 and position 0 satisfies XP1. So this word satisfies XP1 until P2. Look at this word. Here already P2 is true in the very first. So this is position 0. So this word satisfies XP1 until P2. There are many words like this which satisfy XP1 until P2. Let us now have a look at the automaton for XP1 until P2. It has 4 states. In the initial state, there are 2 options. Suppose the first letter that is read already contains P2, then we are done. We go to an accepting state from where you can read any letter. Look at this word for instance. You read P2 and then you keep reading any letter. You don't care about what letters you read after that. Suppose the first letter that is being read does not contain P2, then till you see P2, you have to be seeing P1. Moreover, you can't read just the singleton P2, because if you had given an option of reading the singleton P2, that means the first position does not satisfy X of P1. Okay, suppose I had added P2 here along with this letter, then you could have read the empty letter, the empty set followed by P2. Of course, P2 is true there, but in the first position, X of P1 is not true. So from Q2, you are forced to read a transition that definitely contains P1. The options are either P1 or P1 P2. If you read P1 P2, then you are done, because P2 is true until then X P1 was true. However, if you read just P1, then you keep reading P1 till you see this letter P1 P2. Again, here you cannot see just the letter P2, because then in the last time you take this transition, in that position X of P1 will not be true. So you have to read only P1 P2 and go to the accepting state. Let us look at this word. This word has the empty letter followed by P1 P2, then it takes this transition and then it goes here. Now look at this word, empty letter P1, keep reading P1s and then P1 P2, and then you read whatever you want. Note that suppose here if I replace this letter by just P2 instead of P1 P2, then that word does not belong to this LTL formula, because in this position X of P1 will not be true. Please understand this automaton. Note that this state cannot be made the accepting state, because this will then allow you to accept the word where P1 occurs till infinity and there is no sign of P2 at all. One can make this state and this state as accepting states. It will not matter and the language will not change. However, if Q3 is made the accepting state, then the language changes. Here is another example. FP1 and not of FP2. Sometime P1 occurs and it is not the case that sometime P2 occurs. That means P2 never occurs. Here are some examples. Here is the automaton corresponding to this LTL formula. As long as you read the empty set as the letter, you stay in Q0. The moment you read P1, go to an accepting state, and here you are allowed to read either the empty letter or P1. Nowhere in this automaton you are allowed to take a transition on a letter that contains P2. Okay, so you read empty letter here, read only the singleton P1. Here again you can read either the singleton P1 or the letter consisting of the empty set. This is a non-deterministic Bucci automaton. Yet again, Q0 cannot be made the accepting state, because it will then allow us to read the word that contains only the empty set all along, and that word should not be accepted. Here is a more interesting example. This says that P1 and X of not P1. So initially P1 should be true and then X of not P1, and always P1 if and only if X of P1. That means if P1 is true, then in the next to next step P1 should be true. Similarly, if in the next to next step P1 is true, then P1 should be true now. Let us see. These two force this point to be P1 and here not P1. Suppose this is the first, this is position 0 in the word, position 1 in the word, position 2 in the word. Position 0 should satisfy P1. That means it can be the letter consisting of either P1 or P1 P2. The next position should contain not P1. In the sense it should be either the empty letter or the singleton P2, look at this position. If this satisfied not P1, then this will be wrong, because this says that P1 if and only if XX P1. So here we have P1, that would mean that here P1 should be true. What about this position? Suppose in this position P1 was true. Then this formula says that if P1 is true here, then here also P1 should have been true. But here we have already said that not P1 needs to be true. So here not P1 has to be true. Similarly here, since P1 is true, P1 should be true here. And here P1 cannot be true, because then P1 needs to be true here and true here. Okay, so the only way you can satisfy this formula is to have P1 true in position 0, then P1 false in the next position, P1 true in the next position, P1 false in the next position, and so on. Okay, alternately P1 should be true and false. This is similar to the AB example that we have seen. Hence the automaton for this is, in the first time you read letters either P1 or P1 P2, and then you can read either the empty letter or the letter consisting of P2, and so on. You keep reading this and this will satisfy this formula. There are many words belonging to this automaton, and each of this word will satisfy the formula P1 and X of not P1 and G of P1 if and only if XX P1. Next example, GFP1, words where P1 occurs infinitely often. FP1 says that sometime in the future P1 is true, and GFP1 says that from any point in the word P1 should be true later. So here P1 is true. Again, here P1 is true, here P1 is true. So here f of P1 is true, 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 and so on. So this will correspond to the set of all words where P1 occurs infinitely often. At any point of time, if you see, FP1 should be true. For every position, there is a position greater than that contains P1. This is similar to the automaton for A occurs infinitely often. In a previous unit, we have seen an automaton for the language A occurs infinitely often over the alphabet A, B. Here the alphabet is different. What we need to do is that as long as you see a letter that contains P1, you stay in this state. The moment you see an alphabet, a letter that does not contain P1, you go to another state. As long as you don't see P1 still, you stay in this state. When you see P1, come back to this accepting state. Any run that visits Q0 infinitely often would have seen P1 infinitely often, and any word in which P1 is seen infinitely often would visit Q0 infinitely often. So this is the automaton for GFP1. Here is the next example. This is the last example as well. This says that always P1 implies XFP2. That means along the word, whenever P1 is true, XFP2 should be true. That means in the next step, FP2 should be true. Okay, as whenever there is P1, in the next step, FP2 should be true. Let us now build the automaton for this formula. It has 3 states. As long as you don't see P1, as in the letters that do not contain P1, you are safe and you can read, you can accept the word. We need to be careful once we see P1. Okay, as long as we don't see P1, we stay here, And once we see P1, we go to state Q1. And at Q1, you have to make sure that the next step satisfies FP2. Now at Q1, suppose you don't see P2 yet, you have to keep accumulating the P1s that are being read. In other words, as long as you are in Q1, you know that you have seen at least one P1 in the past for which P2 has not been seen yet. In the sense, we have accumulated the P1s and we are yet to see FP2. So suppose you read P1, P2 first. P1 is true, P2 is true here, but still we need XFP2, right? So in the next step, P2 is left to be seen. Till you read letters where P2 is not seen, the state has to remember that P2 needs to be seen. Now, suppose you see P2, you can go back to this accepting state. This says that for all the P1s that I have seen, XFP2 has been satisfied. However, if the letter that is read is P1, P2, for this P1, XFP2 is still left to be ensured. I hope you understand this. As long as you don't see P1, it's fine. Now you see P1, you need to ensure XFP2 for every P1. However, if you ensure FP2 for the last P1, XFP2 for the last P1, that will do, because if XFP2 is true here, that means FP2 is true here, which means all along FP2 will be true. So XFP2 will be true in each of these positions. What we need to do is to ensure FP2, XFP2 for the last P1 that we read. Here we are reading P1. We need to ensure XFP2. As long as you read letters that do not contain P2, stay here. Now suppose you see P2. There are two ways in which you can see P2. Either just the singleton P2 or the letter P1, P2. If it is the singleton P2, we are done, because for all these P1s we have ensured XFP2. However, if we read P1, P2, we are still left to ensure XFP2 for this P1. So here we need to ensure XFP2 for this P1. If you keep reading P1, P2, then it's still fine, because you are P1 here, here P2 is true, so XFP2 is true here. Similarly, there is a P1 here, there is a P2 here, so XFP2 is true here, and so on. So if you read P1, P2, and as long as you read P1, P2, it is fine. P1 implies XFP2 is true. Suppose you read only P1, that means you need to ensure P2 for this P1 as well as this P1. It is similar to this state. The situation is same as what we were when we entered this state. So if you read a letter that does not contain P2, then go to this state. If you read the letter just P2, then we have ensured XFP2 for everything that entered, for all PIs, for all P1s before seeing the state Q2. Let me repeat the transitions out of Q2 one more time. When you come here, you know that you are yet to see FP2, XFP2 for this P1. There are three ways now. As long as you see P1, P2, you are yet to ensure XFP2 for the last P1. There is one possibility where you keep seeing P1, P2 forever, in which case it is fine, because for every P1 here, there is a P2 here, for every P1 here, there is a P2 here, and there is no end. Suppose you read these letters, ones that do not contain P2, that means for the last P1 that you have read and for this P1 that you have read, you are yet to ensure XFP2. So you have to come back to the state Q1. The other option at Q2 is you read just the singleton P2, which means for all P1s that have been read before taking this transition, XFP2 has been satisfied, and you can safely go back to this state which is capturing this particular situation. This is a fairly involved automaton. As you see that given an LTL formula, constructing the automaton is not that simple. We have given multiple examples. Some examples were simple and examples like these were not so simple. In the next two modules, what we will do is to give you an algorithm for converting an LTL formula to a non-deterministic Bucci automaton. The goal of this module was to give you some examples of LTL formulae and their corresponding non-deterministic Bucci automata. So here is the summary. The LTL model checking question is as follows. Given a transition system and an LTL formula, does the transition system satisfy the LTL formula? In the very first slide, we saw the schema for this LTL model checking. How do we check if this transition system satisfies the formula? You create the negation and then convert the negation into an automaton and check if the intersection of the transition system and this automaton is empty or not. We have seen some examples of converting LTL to NBA. In the next modules, we will see an algorithm that can convert any LTL formula to an equivalent non-deterministic Bucci automaton.